Apagamos una de estas, ¿no? Ahí mejor, yo creo, sí. Se ve mejor.
Bueno. Tenemos hasta las 12:30.
Perfecto. Ok.
Thanks everyone for coming to the seminar. We have this Aburto
Okay. Hello, everybody. I'm very happy to present my work. I'm a new professor of the Faculty of Engineering. Let me talk to you about my background. I've been working in like 15 years before in doing consultancy, working in a lot of different companies, but mainly on solving problems in machine learning, in analytics, basically in retail industry. So this is what I'm focusing on solving two kind of projects or decisions they have. The good thing about the retailing is they have a huge amount of data, that we can use to rely on this information to solve or to support some sort of decisions. Basically, when we talk about this analytics, this is a very good paper from Eric Bradlow about what kind of the decisions we can solve in with big data and predictive analytics. Basically, we have a lot of information about the different customers, this behavior they have, all the sales they got, the kind of different products. But you have to take some decisions about the promotions, about segmentations, also some kind of decisions about the stock, how many products should I buy, or the relation I have with my suppliers about these products, what is the assortment or the portfolio I have in my different stores. Also decision about the stores, the layout, the capacity, how many people, whatever. So basically, we will focus in two kind of problems here, or I will try to show you two problems. First one is about the prices. So retailer have this kind of portfolio of this product, and they want to maximize the performance of the category. And there's a lot of interactions they want to measure, to take into account into the models. So basically, we want to improve this performance of the profit, or the performance of the sales, or the contribution they got in terms of the product category. The second problem I will talk about is about this the customers, and trying to use some novelty methods, use it on text mining. We analyze text. This is another context. It's to analyze text and detect these topics, or what it's the text it's talking about, or how can I relate some kind of hidden or latent topics inside the text. So basically, use a very popular model called latent Dirichlet allocation to detect this kind of topics. We will do the same with the transactions, and instead of topics, we will detect some kind of motivations. Each one of us go every day to supermarket, not every day, but with certain frequency to the supermarket. But each one of us go with different motivations. For example, I will go to buy my monthly reposition for all my house, my kids. But sometimes I go to the supermarket maybe for other reasons. I have to organize some kind of party or some kind of social gathering. So my consideration set on the supermarket is different. The question is, maybe I can analyze this kind of motivations. Maybe I can detect, and second, I can try to use this information to predict other interesting stuff, like the amount, how many money I will spend on the retail, or maybe I can predict what are the specific motivation each one of the customer has in a certain point, using the previous information. And this is very interesting for recommendations, for example. So all the recommendation system works with previous transactions, but maybe I don't want to use all the transactions. Maybe I can predict the type or the motivation that it's censoring or are giving information about the consideration set of product that a certain customer is interested in a certain time. So in retail, we have this kind of huge assortment of data. Different types of data, structured, semi-structured, unstructured data. as I build models, we want to apply some optimization or machine learning models. I will try to apply this sort of transactions. We will use CRM transactional data. Maybe we can use competitor pricing to include into our pricing models, but also this kind of loyalty program, so we can track a certain customer in time and see how this customer evolves in time, or how these baskets modify in time, and we can learn about it. So the first project I will want to show or want to focus is this category pricing optimization using the data-driven constraint. Basically, the setting we are using is this consumer packaged good. So there are products that we bought every week, diapers, pasta, beers, okay? So we're doing some assumptions, maybe strong, maybe weak, but there's no stock out. There's some kind of continuous replenishment. My suppliers, I can trust in my suppliers. I don't know if this week works very well, but I can trust in the long term, they work very well. There's no fashion goods. It's not this kind of products with some seasonal factor that I have to buy, or I have to do this kind of revenue management. This is another setting. The problem here is there is a portfolio of products, but these products, they have a specific thing that there is a huge interrelationship between this product. When I bought a specific beer, maybe I will spend some time to look about what other products are related to this beer, or maybe there is another brand that I can do, or maybe I can try another beer, another brand. But there is a huge interaction between this product. And we can do maybe this is a strong assumption, it's the rest of the product of the supermarket doesn't affect too much what it's happening inside so basically we will study all the framework inside the category, and we will not consider other categories, and we know that there is some kind of interaction. So basically, the intuition we want to define is this concave function, or we want to define this maximum about the performance in price. If I charge too much, okay, I will earn a lot of money per product, but the problem is I will affect the demand. There was a low products that there's a very few products that I will sell. The problem is I charge too less. I do a lot of promotions. I will sell a lot of products, but the problem I will earn a lot of a few money per product. So there is some kind of economical intuition. There is a maximum in this setting. The problem is it's a huge problem in terms of product, of store. I take this decision every week. I need to measure these parameters. So this is we have another people here that it's very dedicated to this, and in the economic field, and in terms of how to estimate this elasticity, the own elasticity, and this cross demand elasticity. So let me talk about this. I was doing an internship on the first semester in Leuven, in Belgium, so I learned a lot about the machine learning models, but also I learned something about beers. So they got this Stella Artois beer, they got the brewery there. But if you talk with a Belgian guy, they say that Stella is not. Okay, they will say that Stella is, okay. So the problem is when you are a retailer and you have to define the prices of these two products, maybe I can reduce the price of the Duvel, that it's a much better beer, and I can do this kind of upselling. People who wants to the Stella Artois and moves to a bigger price, an upper price product. Or maybe I can do the promotion in the Stella, and maybe some people who are sensitive to price, they move from Duvel to Stella because they are only focused on price, and they can switch, and this is called cannibalization, or we are doing a downselling. And this is the kind of things we want to avoid. And this is the kind of thing that happens every day in stores, in all the supermarket chains. But this is something very hard to measure, this kind of cross-elasticity effects. You need a lot of data to understand. You need a variation of the prices to understand how we can track this effect. So let me show you again. So if I do a reduction in a regular price, so there is a switching from people from the premium product to this promoted low profit product. So I increase the sales of the promoted low profit, but I reduce the price. I reduce the price, so I reduce also the demand of the product of the high profit. So the problem is we do promotions, supermarket do the promotions, there's a lot of promotions in supermarket, but always they are taking into account only the product. They're very, very hard to measure what happened with the whole category. And it's very difficult to disentangle all the effects inside the category, just to understand how a certain price affects to other or substitute products. So basically, let me talk about another kind of problems they had. I got exactly the same product by different formats, or there is a pack here, and this pack, they do a promotion on the single unit package, and the single product is cheaper than the pack. This happens also often because the supplier or the category manager deal with or do promotion for a single product, don't take some kind of relationship for the same product or other formats. And this is cheaper, so all the people will buy this single product, and the sales also here will be, so we will have out of stock of this product, and we'll have this no demand for this product, so there's some kind of this kind of problems with pricing. This is what we call some natural relationships. So in terms of there are some things in pricing that always the bigger packs should be cheaper, but sometimes there is some kind of a problem and have this kind of problem in the performance. So this gives the intuition also that there is some kind of things going on this price definition in the whole vector of prices of the category that always happen, and sometimes they break this kind of rules of orders, and we want to learn from data to try to recover this kind of order rules, something that usually bigger formats are cheaper than smaller formats, and we want to understand if this rule breaks or give a better or bad performance when they are not working on. Again, Eric Bradlow. So when we talk about this pricing optimization, this is the general framework. Basically, we build this demand model. We want to learn from data. We load this in transaction information. We use maybe other information from competitor data, price, sales. We got sales from competitors, but at least price. And we can calibrate our demand model, and then we will do this kind of optimization setting. We want to maximize the profit using this demand model, conditioned to some sort of, and our decision variable are the prices. And basically, I can set different scenarios, different objective function. And here is, they're including this kind of concept about these pricing rules. I got my optimal prices, then I can apply and do some kind of experimentation maybe, or applying, and I can turn the process on the wheel. So I got the data, maybe I can calibrate this model. I got here a double log model, and these beta parameters represent the elasticity. So I got this elasticity matrix. And then I can include this elasticity matrix into our function, onto objective function. I can improve the total performance of the model, and I can get some intuition about where I can get this maximum. Okay. So again, the problem is, or the literature is very concentrated on how I can improve the estimation of this function. There is a wonderful paper from Alan Montgomery. He builds very not very complex, but it's a model. It's a hierarchical Bayesian model that it's using information from stores to build some hierarchical structure to calibrate and to estimate this demand function in terms of the prices. Okay, and I do not only support my conclusions about one store. I'm using all of the stores to understand how the people react when I change the price of a certain product. So there's a lot of research in how I can improve this demand function to do the maximization. So basically, I want to do the maximization procedure. I I want to estimate this on price elasticity demand. I got this substitution pattern. I want to improve the upselling. I want to move to the people from Stella to the Duvel beer, and I want to avoid the cannibalization. Okay? But, so let me talk about reality. This doesn't work as we want to. Let me tell you about the problem. So basically, I got this this is an example toy, but look, I got two prices I want to improve. I got this objective function. I got the current price here. So I got this optimal price of the setting. But this is what I expect, and I can improve the price here. I can increase to get the optimal price. But in reality, the optimal price is maybe because of the parameters I got. The optimal price is very far from of the actual price. Okay, or I can some kind of rules. For example, some managers apply this kind of rules. Okay, you don't have to move your price more than 50, more than 30% from your actual price. The optimal value is very far, and it's very far because the estimation of the parameters. Maybe I don't have enough data to support where I can estimate my demand function. And this gives a lot of uncertainty about what is the real objective function. I got a lot of noise. So the problem is when I try to maximize that, I got solutions very far, or some sort of corner solutions in this problem that are defined at the end. I define this final solution, how I define these pricing rules. So if I charge more, or the optimal price, or the decision should be 30% or lower 30% than the actual price, maybe the optimal solution should be increased 30%. But the optimal solution will be defined by these pricing rules, that it's some kind of knowledge, there's some kind of intuition. So the question we want to answer is maybe how I can create these pricing rules. Maybe I can use data to create more intelligent or more data-driven constraints. And also this data-driven constraint give us some intuition about this area, about this closing to the optimal solution. Maybe I can give intuition to get a more robust solution. Let me give you this example. For example, so we use the elasticity matrix from Alan Montgomery, and we got this matrix, elasticity matrix he estimate, and using the first two moments, we make a lot of simulations for different draws of the elasticity matrix. So each point, we take one draw of the elasticity matrix using the media and the variance, and we put this into optimization, and we run the optimization. And we got one optimal solution. And we did this 50, 500 times. So we're telling here is that the solution is very unrobust, or there is not well, we got a solution here, but if you see the frequency of the optimal prices, you can see that there's a lot of corner solutions, or bounded by the constraint we apply. So there is an estimation we got in the research, in the literature about this cross-elasticity matrix, and when we solve the problem, we add some kind of noise in the same level that the estimate noise. There is a lot of variance in the objective function. And the optimal solution also get a lot of different results, also a lot of corner solutions. Okay? So the question is, maybe I can add some kind of constraints based on data that we can focus this point, or maybe here we got a very good solution about the real, or a good interior point solution. So the limitations we got with the actual methodologies, we have problems on the demand destinations. Also, we have endogeneity issues on the demand estimation. Maybe we have other variables that we cannot measure and also are affecting demand, and we are confusing prices effect with other kind of issues. For example, out of stocks. There's a complex of the model also. There's a wrong parameters in the elasticities. Maybe I can estimate some positive elasticity, so I increase the price. I will increase the demand, that it's maybe counterintuitive. There is a lack of the information maybe that affects the demand. So also there I got some problem on the optimization. I got local maximum. I got solutions very sensible to this restriction. I got problem with the stability of the solutions. And the question we want to address is how we can define these constraints. Okay? So that's the scope of the project. And also I want to tell you that this is a problem in the industry. Talking about pricing rules, there's a lot of software development, or there's a lot of solutions that are solving this problem, price optimization. I will be burned outside if I will talk about how to improve the performance of supermarket. Maybe it's not good time for talking about this right now, but maybe I can talk about how we can deal with better promotions, how we can address to people who are sensitive to price. I don't want to spend promotions to everywhere. I want to focus my resource that I limited to each specific products or customer that are sensible to that. So there's a lot of software working on that, and all the software talks or use this kind of rules or constraint to define which pricing rules should I define. For example, this clear demand and retail pricing has rules. And also, so the manager have to impute some kind of information about these rules on the IBM. Also talk about these pricing rules. There is some kind of information that the managers have to address in the optimization to put or to calibrate the model. So how we will do this, let me give you first the intuition. First is we will try to reduce the feasible set solution with tiger business rules. So for example, we were talking about the data of the prices. Maybe I don't want to see the price all the range or the dominio I see before on the history. Maybe I can reduce, and I say reduce the actual prices in some sort of box from the actual values. Second, I can apply non-trivial business rules or relationship between products. For example, okay, Duvel beer have to be always expensive than Stella, or Duvel beer have to be always expensive in 2 euros than Stella. I can get some kind of non-trivial business rule to reduce this feasible set solution, to know where maybe we have better solutions. And also, I can look about this is the most important work about this, it's to understand price structure and how this price structure is correlated with performance and profit. So basically, we will measure the profit, and we will see a distribution of the profit, and we will see which scenarios leads to better profit. And we will try to understand which kind of rules are correlated with high profit scenarios. So basically, we will have this kind of data. I will use constraints about where I have more data, and I will use other kind of rules that are based on simple correlation. And basically, we will use some kind of machine learning methods called association rules to run in my database, use this, and track all these rules, and we will put all these rules into our framework or into our optimization framework, and we will see what's going on. And hopefully, we can have not better result, a more reliable result. The problem is that when I run the optimal solution, I will have a solution here that it's 1000% better, that nobody believes. I want a solution that I can improve, or something that it makes sense in terms of what I know, or it's close to the actual values. Okay, and this is the optimal solution. So basically, we have this the original framework, and we will add this omega space where we will find when we will constrain the space of the optimization. And basically, we have two kind of rules. First, this is order rules that are consistent with what managers have decided before. So I will apply some kind of rules that are supported by data. I don't want to do something fancy that never has happened before. Second, I will apply this kind of concept of correlations or lift or confidence in terms of the restriction, that when I apply this restriction, I have, in terms of probability, I have more probability of have higher profit than the average. Okay? So how does it work? Okay? So this is market basket analysis. This is the paper, the Agrawal. This Agrawal, it's a very large database conference that he presented this paper actually in Chile in that year. This is one of the most popular, more reference paper in data mining literature. This is a starting, what he created this kind of a search method for multi-combinatorial problem in terms of what are the correlation between a big number of columns in terms of occurrence. So basically, he tried to solve this kind of market basket analysis and measure if there is a relationship between product X and product Y. Basically, he created this framework or tried to measure these three index: confidence, support, and lift. I don't want to go in detail, but what I want is some kind of, I want to detect if something happened, what they produce, so there is a huge correlation with some other effect on Y, for example, okay? So in translating this market basket analysis in our setting, this is the kind of things we will solve. We have some kind of pricing rule. This is, we solve more than this. We solve some A multiplied by P greater than B, so it's more than this. This produce some kind of the profit of these two products are greater than the average profit. We want this kind of rule that improve or have some kind of production in terms of the profit. And we will produce this for three different levels. First, we will control the average price of the product, or the sum of all the prices of the category. We will do for individual prices, and also we will do some kind of distance between two prices of the category. So how it looks like? Okay, here I got the order rules. Here is an histogram of the actual, for example, this is the average of a category. And I got the density of the, so basically what it's saying that maybe if the order rules, you should charge over this price because there is very few information lower than this price. So I will charge all the kind of prices when I will that are feasible are the kind of prices I saw a lot in the previous history. I got a lot of information to say something about it. The second, okay, these two constraints. Okay, the second should be these performance rules again with the price, and they say, look, if I look the profit against the price, the average price, when I got a price greater than this, I got a higher profit compared with the mean or the average. So basically, if I put this the average price between these two or greater than this, I got a better average price than the rest. If I look at a certain brand or a certain product, I got exactly the same, some kind of order rules that are binding the price where I observe. I don't want to charge something very unusual that I don't rely on what's going on with the demand. And second also, I got this kind of application in terms of for the performance. If I saw the profit, look, the average profit inside here, it's better than the outside of the constraint. And also, I can do exactly the same for distance between two products. Okay, and I can constrain the distance and all the distance between these two brands. So basically, all this search space, I can apply this algorithm. I can apply this into this price structure and look about all these rules, and I will have these two sets of constraints that we can use to. So this is the kind of constraint that if the distance is between these two products, okay, I got 95% of the support, so I got a lot of information. This is the average profit when these rules happen, and this is 64% bigger than the average. Okay, so I got a good rule. We will select this kind of rule. We have better performance on that. Look, this other rule here, for example, I got a distance between two products. I got a lot of data, but the problem is when I apply this rule, I got lower profit than the average. So maybe it's not a good rule. Maybe it's not. Maybe it's not. So basically, we apply this algorithm and we extract these rules, and we will see what's going on with the optimization. We apply this to this is we got a supermarket database when we do all the research, And here it's pretzels. I don't know why we use pretzels, but pretzels, okay? They got a lot of data information about sales, about prices. They do a lot of promotions. We can build demand models, and we can apply these rules and see what's going on there. We built 3 models to predict the demand. It's, this is a traditional double log regression and ordinary least square to estimate the elasticity matrix. We use the hierarchical Bayesian model using a pooling of information of all the stores of the supermarket, and we use with this L1 regularization to reduce the number of parameters, okay? To remove something that it's not strong enough, okay? So we have this L1 regularization. Basically, you can see some specific point, but models, 10% of error, it's sort of okay. So let me show you the result. This is the profit I got. This is the actual profit on the last month. You can see this, this is the forecast by the 3 different models. And this is the optimization results. This is the number of constraints I apply. We will always adding new constraints. So here we're using 30 constraints to lower an upper bound for the 15 products we have on the category. And you can see if I maximize this, this is the actual profit you get. So we got this kind of solution here on the, okay? So we're saying that we have this problem, we solve, and if you don't apply, or if you apply some very naive rules, you will have whatever. You will have very weird solutions and this improves a little bit when I use a better or more robust model. It's 160 and 200, but again, this is 400 better than the actual solution. It doesn't make sense, right? When I add all these order rules for individual price, for the pairwise comparison, and also the mean, I move from 30 to 400 restriction, and now we have something that it's more on the track. So first, if we use simple historical price ranges, it's not enough. When we add the rest of the order rules, we reduce significantly the price space. But when we add these performance rules, now we got some kind of reliable solution or something that from 31 increase 9% or 5%. This is something more reliable in terms of the actual solution or something that makes sense. And this is the solution here. When I apply all the rules, you can see that if I use something simple in terms of the demand model or something more complex, I got some sort of the same solution, or the results are reliable for all the models. This is another result. If I apply, for example, what are the, managers can do terribly or they can do very wrong decisions. So this is instead of running the minimization, we do what are the worst scenario. What if, sorry, in terms of doing the maximization, we did here a minimization. What are the worst thing that a managers can do? And of course, if I don't got any restrictions, I can reduce this very far. I can do terribly, or I can put very bad prices, or put everything in low prices, okay? So the performance rule or order rules also works to avoid these bad scenarios. Also works as a constraint to you can avoid to do terrible things in terms of the solution. So basically, instead of looking the good pattern behavior, good prices, we are cutting the space of the solution that have bad performance. And if we run the solution, or the worst solution here is actually better than the actual. So this is saying that maybe they're doing some kind of naive decision in some of the products that are reducing the profit. So when I apply all the rules, you can do it better actually than the actual solution. This is the worst thing you can do. Let me come back to the robust analysis. We got our elasticity matrix, and we do exactly the same problem we apply on the beginning. We add noise. So we for the mean and the deviation we estimate on the matrix, we applied some sort of noise. We ran some draws, and for each draw of the elasticity matrix, we run one optimization. We take a lot of time, but you can say that here we have 4 analyses, 4 different scenarios. One, this is using only, using rules from the, I will put the prices between 0 and 100% of the support. So I will only prices on the observed prices before on the transactional data. Then the second scenario is the initial price box. I put the initial price I got, and I move only 30% from the actual values. And then I will apply all the order rules, all the performance rules. And you can see how there is a lot of variation in these 2 scenarios on the prices. This is the optimal price for these different simulations of the elasticity of the objective function. So you can see that again, if you apply very simple rules, you don't have a robust solution. But this is a good delivery in terms of our pricing rules that are giving a very strong or limited solution that give us a better solution. You can see also if I normalize all the prices and I can see this box plot about all the deviation, we can see if I apply all the rules, I get a very certain precision on the decision I have on the final solution. So just to end this first part, as if we explode the transactional database, we can extract this constraint. And there's a lot of information there. We focus on improving always our objective function and to get more reliable parameters. But here is another intuition in terms of how with data, instead of improving our objective function, maybe we can create more meaningful constraints. Okay? Trying to understand where we can find these high probability scenarios of profit. Okay? And also, we want also some cutting planes, some restrictions where I get a lot of data, where I can get reliable decisions. So we got these order rules, these performance rules, and also these business rules can complement the demand models. In terms of the, when we present this, there's a lot of another interesting feedback we received that the managers don't understand much a parameter, what does it mean. But when I talk about when I talk about the double beer or one product should be higher than this in this distance, this is more meaningful for them to understand that, oh, these are the top premium product, or I should chart this distance for these other products. This got more meaningful for them than some kind of elasticity or cross elasticity parameter. So the rules, also this constraint, it's another meaningful way to understand what's going on inside the category and all the relationship between the products. So we got a robust solution, and it's useful to avoid this by the scenario.
But don't you run the risk of maybe become overly constrained, and you don't have much space to move your price, then you just keep doing the same thing over and over again because you don't have space to move. Never get outside the box, so to speak. Isn't that a danger of doing that?
Sure. We would love to move out. The problem is we have this kind of trade-off. But if we move out of when we go out, we have less data in terms of I don't rely much, or I got more. My confidence interval about this solution, about the profit, I don't rely much about this solution. So basically, we have this trade-off. The kind of solution we apply, maybe it's over-constrained, but I want this kind of reduce the uncertainty on the response I'm doing about the decisions, about the optimal solution. Maybe it's a problem, I can understand, but it's some kind of problem we are looking on in terms of the robustness of the solution we want to give. Okay? There's another interesting thing, it's how these rules compete each other, or which one of these rules are active or not, or maybe there's some rule that don't add information. This is something also we can discuss and to try to clean out or understand which are the good information constraint that give us information for the final solution. Also, maybe this is something interesting to highlight.
Would it be useful to have some budget in some days where you can change prices arbitrarily, maybe in only one supermarket, so you can gather information
Sure.
from other places?
Sure, sure. I didn't talk about this set. There's a third set we have. We have this order set, this performance set, and we have this something called this discovery set. That are prices that indicate us, hey, guy, if you apply this pricing, you get a lot of solution, a very good solution in terms of profit. But we don't have enough data, or we don't rely much about this data. And actually, this kind of solution or constraint are very useful for what you're saying, Javier, in terms of to do some kind of price experiment or to explore. You know this kind of problem of the multi-armed bandit, where to do exploiting or to discover new prices. So here the rules are also giving us information where we can have a lot of profit, but don't have enough support, are giving us intuition in terms of this kind of spaces.
And what do people, farmers and managerial people, think about this possibility?
Sure. This is the interesting thing. Yes. They do a lot of experiment. It's very cheap to do some kind of experiment. Here it's just changing the prices and look about wait for the time and see on the result. The question is to understand what is the counterfactual. What will happen if I won't change? And it's very easy to do that. You got apply this kind of in control stores. So you apply it into this kind of some store where I got similar store, and I can write some simulation. I can run some experiment to understand the effect. These pricing rules, I think, give a lot of intuition where we can run the experiment. How much time? I'm not sure. 6 minutes. Okay. But let me explain this about but because this is very interesting, or this is the actual work I'm doing also. I talk about this purchase motivation. So the same customer, exactly the same person, when I go to the supermarket, I go for different reasons. And when I go for different reasons, my price sensitivity, the promotions I should be interested in are different. Exactly for the same person. For example, if I go a Friday night, maybe my consideration set of products is different when I go Saturday morning, where I have to buy for all the month, or I go with my wife or the kids, and it's different. Okay? So the question is, can I detect this? Can I identify this kind of motivations? Can I use this for taking some information decisions to improve promotions or to do some kind of decisions? So basically here are category management, and category management try to group the products. Yeah?
Yeah, one question. How do you work with the corner shops now? Because I don't go anymore to the supermarket.
Okay, there is another. Perfect. You don't go to, that's very interesting. Corner shop got information, and now corner shop is another leader, it's another jumbo. So corner shop also got information about each one of your purchase and can understand your motivation. And corner shop also can give you promotions. And maybe the promotions they can give you can be different if they can predict that you are in a different mood or a different motivation. What are you buying? That's the kind of consideration.
The motivation is I decided to host a party this Saturday, or outside because this weekend it will be the national fest. So
okay.
Will have some motivation, and I think it's easier to predict.
That's easier to predict. We want to predict your behavior. We want to analyze your past purchase and to understand that if it's a Friday night, if you come 2 days before to buy all your things, all your monthly reposition, if you come 2 days later, it's hard that the probability to buy again, it reduces. So maybe your motivation is different. So basically the idea is to adapt the probability of to belong to each one of these motivations, to adapt depending on some temporal variable and previous information. Basically, how does it work? Actually, right now, there is some kind of promotions that we receive on our mobile phones. And these guys have some kind of routers or sniffers that detect our MAC address. They detect that we go inside just go inside. And this gives them information about timing and that we are there. And if we are there, they can put some kind of warning or email to notice that you have some kind of promotions or to adapt what we are looking for inside the store. This is the kind of decision we want to improve. So basically, the complexity here to decide about the category management or how to, this is the divide and conquer. This is what the supermarket divide all the categories. We want to use some more complex model to try to analyze this cross-category dependence. We don't want to analyze this each one of the categories independently. We want to understand the relationships between products. And we will use this LDA model. LDA, what it does is a direct distribution. We learn from data and we detect all the words and we do the words distribution in documents, and we say that there is a relationship between words. And we repeat this, we saw this pattern that it repeats in the documents, and we identify this as a topic. And we can identify topics that repeats on different documents, and we can understand the probability of each one of the words for each one of topic. So for example, here there is one topic talks about river, stream, and another topic talking about banks, loan banks, okay? Because these two words are together in the document. Basically, we will do exactly the same in transactions. So for now, each one of the transactions should be a document. The documents have words. No, we don't have words, we have products. And we will see the relationship between products, and we try to estimate, to calibrate this direct distribution between our products. And impressively, it works. We see some natural, or we can give a meaningful relationship to the distribution or to the categorization from the different products. So we got these tickets, and instead of topics, we will call these motivations. So basically, how does it work? We have a direct distribution for theta sub m. Theta is the probability for each transactions to belong to the motivation. Phi sub k, phi represent the probability for each word or each product for each motivation to belong to each motivation. So how that the data generation process for each purchase, I sample set sub n, that it's a multinomial from theta sub m, that it comes from the direct, and then given the topic, I sample with probability phi sub k. I sample the product that it's on the transaction. So I only depend on these alpha and beta parameters. Alpha, it's very interesting because it's saying about its information. It's the hyperparameter for this direct that it belongs to talks about the probability for each topic inside how is the distribution of topics inside each one of the transactions. So maybe I can do it more fuzzy, more crispy, I can control this with this alpha. Or I can do an alpha sub m. I can do some specific alpha for each one of the customers. So we have again the same data set. We can use this, we can use some kind of information criteria maximization to balance the number of topics I have and also the performance in terms of explanation or the log likelihood of the data. And basically, we can maximize this in 5 different topics. And we understand and we find these 5 different topics on the data set. We have this perishable, people buy this kind of set of perishable products, some kind of general food or groceries, this prepared food, frozen pizza, frozen meat, and also like the rest. This is very interesting. There is some kind of relationship between this product. We call it hedonic or something. It's not for the house, not for the family. It's for myself. I want to spoil myself with ice cream, beer. I don't know. Okay, but impressive. The transaction goes with a lot of product of this basket. Okay, so it's impressive how there is a direct distribution that we can calibrate, and there is a strong relationship between these products. Okay. This is very interesting because we do the market basket analysis and we can do pairs It's very hard to measure more combination with more product. Here we do we can see the track of the old products. It's not just pairs. We are comparing the distribution of belonging for each motivation for all the different products. How we will use and I finish with this, we can use this LDA with the theta parameter. We can calibrate and estimate another outer variable that, for example, should be the amount of the transaction. Okay? And we can calibrate exactly our Bayesian framework with using theta. So the output of LDA should be the input for this regression, and we can calibrate and estimate this rho. What means this rho sub k? Rho sub k, it's how a motivation, how it's important to calibrate or to predict, for example, the amount of the transaction. Or the most important, interesting thing that we are trying to do is to use information about the transaction to calibrate the hyperparameter alpha. For example, here we are trying to use a multinomial logic to calibrate and to use, for example, the day of the week of the hour of the transaction, to understand and to modify the hyperparameter of the Dirichlet distribution to say that, for example, if you are Friday night, maybe the alpha related to party or to hedonic product should be higher. So you have more probability to have this kind of motivation. So basically, the idea is to use timing or previous information about the transactions to calibrate this alpha and then put this alpha onto the LDA Bayesian framework we are using. So that's it. Thank you.
We have -4 minutes for questions.
-4. Oh, sorry. Interesante. Que se responde en español nomás. Qué interesante. Efectivamente, mi compra está de alguna forma condicionada por el layout o por cómo están los productos o si hay o no un producto. Muchas veces hoy día yo me encuentro y no hay cierto producto y tengo que reemplazarlo. Claramente que ahí uno podría usar, hay cierto condicionamiento. Lo interesante es que uno podría aquí de alguna forma condicionar eso, colocarlo como un hiperparámetro o decir esto yo podría correr el LDA para una tienda y entender qué pasa en esa tienda o qué motivaciones hay en una tienda. Efectivamente las tiendas condicionan el problema. Hay tipos de transacciones de productos frescos que son compras más baratas, más chicas, con menos productos. ¿Ok? Son compras más frecuentes. Y ese tipo de compras se producen en supermercados más pequeños, convenience store. Al contrario, estas compras de groceries son en menor proporción en eso y más en hipermercados, donde hay más assortment, más tamaño y puedo comprar, tengo estacionamiento, en fin. Por lo tanto, efectivamente, el tipo de tienda me condiciona los tipos de motivaciones que veo y eso se ve, por ejemplo, en la probabilidad por defecto en la probabilidad promedio, digamos, de que cada transacción pertenezca a una motivación. Correcto. Lo interesante es que LDA recoge eso. Yo podría medir eso de alguna forma.
Okay, thanks a lot, Luis.
Listo.
Buenas tardes. Funcionó, así que...
Funcionó. Hoy bien, se te ocurrió una cosa que la teníamos pensada, pero que no la había mostrado.